Welcome back to Physics 152 Online. Next, let's turn our attention to how to calculate the energy that's stored by a capacitor. When we talked about what a capacitor is, we said it was a device to store charge and therefore to store useful electrostatic energy. So, if we connect a capacitor with capacitance C to a battery that has a potential difference VF across its plates or across its terminals, then when we close the switch, the charge will begin to flow out of the battery onto the capacitor plates. So at some time before it reaches its final potential difference of VF, at some time the potential difference across the plates will be V, and the charge on the plates will be plus and minus Q, which is not the final charge, but just what it is at that instant. So at that point, it will require an amount of energy that we can get by the expression U equals QV, or du is V dq. It'll be that amount of energy required to move a small amount of charge dq across the potential difference V, which is basically saying that we have to use energy to push this amount of charge uphill in potential from the battery to the capacitor plates. So we can set up an expression to calculate the total energy by adding up this quantity du from Q equals 0 when we close the switch and the capacitor starts charging up to the final charge, big Q. So here's the picture. We imagine that at some instant in time, the potential difference across these plates is V, which is Q over C, and then to add an additional amount of charge dq would cost the amount of energy du is V dq. So delta U then would be the total amount of potential energy that it requires, the potential energy change that's associated with moving all the charge from the battery to the capacitor plates. So the integral of all these quantities du is V dq, so we plug that in. We can see now that Q is the variable, and we go from Q equals 0 when the capacitor has no charge on it to a final value of capital Q. And V, we know by the definition of capacitance, V is equal to Q over C. Remember that C is Q divided by V. So we just solve for V in this, substitute into the integrand. We pull outside 1 over the capacitance value because we know that's a constant, and what's left is a very simple integral Q dq, which gives us Q squared over 2, and then integrating that from 0 to capital Q gives us a very simple result for the potential energy that's stored in that capacitor when it reaches its final maximum charge. And what we can do is substitute in this expression Q equals CV, and that will give us, if we just allow V final, we'll just call that V, the battery voltage. So if Q is equal to CV, we square that term and simplify it to get delta U is 1/2 CV squared. You might notice, although this is a completely different physical system, you might notice that this bears a resemblance to the potential energy that's stored in a spring, which is 1/2 kx squared. And the quantities mean different things, but it turns out that mathematically there's a very strong resemblance to the storage of energy, electrical energy in a capacitor, and the storage of mechanical energy in a spring. All right, what about adding together or combining in an electrical circuit two different capacitors? There's basically two ways to do this. We can add two capacitors in parallel, or we can do it in series. So let's look at the parallel combination first. The actual device, as you schematically understand what a capacitor is, it's composed of two parallel plates, and here we assume now that we've connected these two capacitors together in parallel. You can see why the name parallel is used because of their arrangement. Their plates are parallel to each other, and the two capacitors line up parallel. We imagine now that we've connected this to a battery across terminals A and B so that there's a final charge Q1 and Q2 across on the plates of the two capacitors. And these capacitors have different capacitances, C1 and C2. So the top sketch is more like what it might look like if we opened up the capacitors and saw their plates. The bottom sketch is the typical schematic where two short parallel lines are used to indicate the capacitor. So what we can observe, first of all, before we figure out how these two capacitors behave together in series, we can see right away that the potential difference across the two capacitors is the same as that of the power supply. And the reason for that is that if we look at the two dots on the top and the bottom of capacitor C1, those are connected to points A and B just by wires. The dark lines here represent good electrical conducting wires. And we know that inside a conducting wire there's a zero electric field, so that if we were to calculate the potential difference between those 2 points, they're at the same potential. The potential difference would be zero. So the potential difference VA minus VB is the same as the potential difference across capacitor C1, and we'll call that V1. The other observation that we can make, and this is really just a matter of what we call the law of conservation of charge, if we realize that what's happening is a total amount of charge is leaving the power supply and then getting deposited on the two capacitor plates. Well, as charge flows, let's say, out of point A, and it reaches the dot here, it can do one of two things. It can flow down onto capacitor C1, or it can flow to the right and end up on capacitor C2. And the total amounts of those two charges have to equal the total charge that left the battery. And so we can write down simple mathematical expressions to express these two observations. Number one, VA minus VB, we will just call that V, because that would represent the voltage of the battery, and that's the same as V1 and V2, because these two circuit elements are in parallel. Secondly, this expression of the conservation of charge says the total charge leaving the battery, capital Q, is equal to Q1 plus Q2. We'll use these equations in just a minute. So with these observations, we can draw up an equivalent circuit that takes the original circuit indicated here, including a battery, and replaces it with a single equivalent capacitor. So the idea is, can we write down an equivalent circuit where we have just one capacitor that has the same effect as these two in parallel? So our goal now is try to find an expression for C equivalent in terms of C1 and C2. Is it equal to their sum, or could it be something different? Well, it's easy enough to figure out just using this expression for the total charge. The total charge leaving the power supply is equal to Q1 plus Q2. Q is equal to C times V, right? So we can write down the Q that would be coming out of the battery and getting deposited onto the equivalent capacitor. Q on the left-hand side is just C equivalent times the V of the battery. Q1, of course, is C1 times V1, but V1 and V2 are the same, right? So this is actually C1 V1, and the second term is C2 V2, but V1 and V2 are the same. So I've simplified it already, and if we just divide both sides by V, the potential difference across the battery, we get C equivalent is C1 plus C2. So when two capacitors are connected in parallel, they can be replaced by a single capacitor which has the value of just the sum of those two. Now, let's look at the series combination. Once again, we can make two simple observations that will allow us to calculate the equivalent capacitance that we could use to replace these two. They're in series, right? Because to get from point A to point B, which is where the battery would be connected across those 2 points, you first have to travel through a first capacitor to get to point M, and then through the second capacitor. So they are serial. They are one after another. We call this a series combination, and it's indicated schematically on the right. What are the observations here? Well, think about what happens when we connect points A and B to a battery and close the switch. Charge begins to flow from the battery onto the top plate of the upper capacitor, and negative charge, if we imagine, just for the sake of argument, that positive and negative charges can both flow out of the battery, negative charge would come out and it would deposit itself on the lower plate of the bottom capacitor. But then in response to that, there's going to be a separation of charge in the region that connects the bottom plate of the top capacitor and the top plate of the bottom capacitor in response. And in equilibrium, what has to happen so that charge would reach its final value and would not flow anymore, we have to have the same charge value on the plates of the lower capacitor as there is on the plates of the upper capacitor. So plus minus Q, plus minus Q. Even though these capacitors have two different capacitance values, they would have the same amount of charge. That's an important observation. And then we can say that the total potential difference, or the total voltage from points A to B, is the sum of the voltage across the two capacitors. The reason for that is, if we remember the definition of voltage, it's minus the integral of the electric field dot dl from the initial to the final point. So if we want to go from A to B, we first have to go through capacitor 1. So the voltage across that would be V1. And then we have to go across capacitor 2, and the voltage across that would be V2. So those two steps take us from points A to point B, and therefore the voltage VA minus VB, which we will call V, is equal to the sum of V1 plus V2. So these two observations can be written down as follows. Q is Q1 is equal to Q2, like we said before, and VA minus VB, which is just the voltage of the battery that we connect this circuit to, is equal to the sum of the two voltages. So if we want to replace the series circuit with an equivalent capacitor, what do? Let's use the voltage equation. V across the battery in the equivalent circuit is equal to V1 plus V2. Well, we can now replace V with Q over C. Q is the total charge coming out of the battery divided by C equivalent. That's the left-hand side. The right-hand side would be Q1 over C1 plus Q2 over C2. Well, we know that Q1 and C1 are the same, according to our observation about capacitors in series. So that's Q over C1 plus Q over C2. Right and the left-hand side both have that quantity Q, so if we divide both sides by Q, we get the following arrangement that relates to the reciprocals of the capacitances. So two capacitors that are in series, their capacitances combine by saying 1 over CEQ is 1 over C1 plus 1 over C2. So that's a series combination. These two formulas are very useful in simplifying more complex circuits. And it's important, though, to remember these observations, because it's not enough in order to answer the kinds of questions that we want to know, such as how much charge is there going to be in each capacitor when we have a complicated circuit. It's not enough just to remember those two equations. You have to remember the observations. When two capacitors are in parallel, the voltage across each of them is the same. When two capacitors are in series, the charge across them is the same. And we'll show an example here. Here we've got a circuit that's not too complicated. It's only got 3 capacitors. 2 of them are arranged in parallel, and then the other one is in series with what would be the resulting combination of the first 2. So let's try to figure out what would be the charge stored on each of the 3 capacitors, and if we know that, then what's the energy stored in each capacitor? So what are we going to do first? We're going to try to replace these 3 capacitors with an equivalent capacitor, because then that will tell us how much charge flows out of the battery. So here's the strategy. We do this, though, in 2 steps. We replace the 2 and 4 microfarad capacitor with a single equivalent capacitor, and then we'll replace that one and the 3 microfarad capacitor with another equivalent capacitor. So the first step is take the 2 and the 4 and replace them with a single capacitor that we will call CEQ1. Those two are in parallel, so we know that their capacitances add together to give 6 microfarads. So our C equivalent 1 is a 6 microfarad capacitor. Now what do? Well, now we want to take that 6 microfarad and the 3 microfarad capacitor, which are now in series, and replace them with a single capacitor CEQ. All right, so that means that 1 over CEQ, because these two are in series, 1 over CEQ is 1 over 6 plus 1 over 3, and if you do the algebra, actually it's more arithmetic, you get 1/2. So CEQ is equal to 2 microfarads. Now notice these 2 sketches, we've already incorporated one of our other observations. When you have 2 capacitors in series, they have the same charge on them. So the charge plus and minus Q that's on the 3 microfarad capacitor is the same as the charge plus and minus Q that's on this equivalent capacitor. And as a result, when we calculate the Q on the 3 microfarad capacitor, it's the same as the charge that's on this equivalent capacitor that's drawn in the upper part of the circuit. So CEQ is 2 microfarads. Let's move on. Now we can find the total charge Q out of the battery, and notice that total charge that comes out of the battery is also the charge that's on the 3 microfarad capacitor, like we showed in this sketch. So that's an easy calculation. Q is equal to C equivalent V, where V is the voltage of the entire battery. Let's go back and take a quick look at that. Right? We said the battery had a 6-volt potential difference across it. And so 2, which is the equivalent capacitance, times 6 is 12. And that gives us the charge Q3, which is also the total charge coming out of the battery. We can't directly find the charge on the other 2 capacitors, although we know that the sum of them has to be this 12 microcoulombs. But we can first find the voltage across them. How do we do that? First, go back to our sketch. The equivalent voltage, VEQ1, which, if I go back to the sketch, VEQ1 is the voltage across this upper equivalent capacitor. So we can easily do that by taking the total charge divided by the capacitance. We know that total charge was 12 microcoulombs. We know the equivalent capacitance was 6 microfarads, so that's 2 volts. That means, if I go back for just a second, now we have found out there's 2 volts across that equivalent capacitor. Or there's 2 volts across the 2 microfarad and the 4 microfarad capacitors. 2 volts across those. So that'll allow us to find those 2 charges. 2 volts times 2 microfarads is 4 microcoulombs. 2 volts times 4 microfarads is 8 microcoulombs. So now we have all 3 charges. We've got 12 microcoulombs was on capacitor C3, and then 4 and 8 was across C2. And there's a good check because we know that the sum of Q2 and Q4 has to equal Q3. We said that already. So that's a useful check on our work. Finally, we'd like to calculate the energy stored. First, we need the voltage across the 3 microfarad capacitor, but that's easy because if we look back at the sketch, the voltage across the 2 capacitors that were in parallel was 2 volts, and 2 plus 4 gives us 6. So 6 was the voltage across the battery. So those 2 have to add together. Since we know that V1 and V2 were 2 volts, then V3 has to be 4 volts to add up to 6. That means we now can calculate U3, 1/2 C3 V3 squared. We have all those numbers. That gives us 24 microjoules. And finally, U2 and U1 can be similarly calculated because we know those voltages and we know those capacitances. So we get 4 microjoules and 8 microjoules. And one final check. If we add all 3 of those energy terms together, we get 36 microjoules. That should be the total energy that would have been on the single equivalent capacitor. And we knew that that capacitance value, we figured that earlier. So we can check one last time and write down U total is 1/2 times the C equivalent times V squared. Well, we found that out before. The V of the battery was 6. The C equivalent was 2, right? So 2 over 2 times 6 squared is 36, and that checks. So the total energy stored on each of the 3 capacitors added up is the same as what we would get if we replaced them by a single equivalent capacitor. So there's a lot here to digest, and we'll work some more examples in class. I'll see you there.